All right, so hello everyone, and thank you for your time during your lunch hour. I hope you still get something to eat after this presentation. It's only 20 minutes. It's a sponsor talk, so you will hear me say Grail Enterprise a few times, but mostly it's very neutral and not a sales pitch at all. I think it's fair to say that engineering teams and every engineer strives to be productive. Right? Whether it's a build engineer, a system engineer, an infrastructure engineer, a developer, we all want to make good use of our time. We want to deliver results, and we want to do so at a high pace and with little obstacles. Right? But the reality is, engineering teams and engineers are rarely productive. Right? There are too many obstacles in our way. And even if you ask engineers, did you have a productive day? Well, some might say, yes, I did. But even in those cases, they might not even know anymore what it is to be productive because they're so used to all these inefficiencies they have to deal with every day, which is also some kind of survival strategy, right? And this is not to blame anybody at all. A major contributor to unproductivity is your tool chain, right? It's from making a change in your IDE or wherever you make the change, that change being produced, being verified, being deployed, and so on, very unproductive in general. Right? A lot of things can go wrong. A lot of things take a long time. Right? And even worse, most engineering teams cannot quantify that unproductivity. How much does something make them unproductive? Right? Which means whenever you try to address it, what do? You just use your intuition, right? You use anecdotal evidence. Or whoever screams the loudest, that's the decision you take. Maybe you have somebody like that on your team, or maybe you are that person, right? So what we need is we need data. We need data about how our tool chain is built. Right? If we have data, we can make informed decisions what to keep and what to improve. Right? We need to know what are our slowest tests? What are the most flaky tests? Why are things happening differently on CI versus locally? Why do the queues on CI, why are they so long? Right? Why are certain dependencies resolved? All this data we need to surface to operate with it. Once we have that data, like I say, we can analyze that data, we can make informed decisions. What do we want to keep and where do we want to invest time? Right? It's going to be an informed decision that we take. In addition, and that's really important as well, it's pretty obvious you can make 100 improvements, right? But what will be the impact of those changes? If you don't know what the impact will be on a given change, it's very speculative where are you going to invest that time, right? If you have to choose between different things, you want to invest where you get the most bang for the buck. Right? In addition to that, once you have a lot of data about what's happening in your tool chain, you can very fast get to the root cause of your problems, if you have problems. Right? Something's failing, something's not working as expected, or behaving differently here than over there. If you have that data, you can quickly get to the root cause. And once you know what the root cause is, it's usually easy to fix. Right? I think most engineers experience this all the time. The problem is figuring out what's going wrong. Once you know, then you can go about fixing it, which is usually the easier part. And so we need a tool that aggregates that data. Many people build their own tool. That's fine. Or you can use an existing tool. But what the key is that you capture data, and you capture very deep data. And so when I say capture data, I don't mean just logs. Right? Logs, very unstructured. It's just a bunch of characters in the end. You need very deep structured data because then you can really reason about it. It's modeled, and you can then make decisions based on that. Right? I pasted some examples here. I can also show one of them live in a second. Is, for example, dependencies. Right? Many projects have a lot of dependencies, and it can easily turn into dependency hell. Right? You build your project, and you're not really sure why it's failing because you're not even sure what dependencies are being pulled in, maybe using snapshots, maybe using dynamic versions. So understanding exactly what is the resolved dependency tree makes it feasible to even understand what was happening and then understanding the root cause. Or you have failures on CI, but you cannot really understand, well, which failure is happening the most, which one is the most impactful, right? And if you have a view like down here, where we just aggregate failures by type or by a certain error message pattern, we can see, oh, this type of failure happens a lot more than another type of failure, right? And based on that, we can then take decisions, right? Maybe you realize, oh, we have one agent where a lot more builds are failing than on any other build or any other agent. Right? Or, for example, here, flaky from the Spring project, right? Spring project, they're using Rail Enterprise. Let's see if they have flaky tests. Because if you ask people, they probably say, no, we don't have flaky tests. Or they say, rarely. But if you have the data, you can really make a decision based on that data, an informed decision. And you will see, well, that they do have flaky tests as well. But not only do you see that they have, but you see which ones they are. And once you know, you can fix it. Right? And you can see what the impact is. How often is it failing? How often is that build even run with those flaky tests? So you can decide, well, which one should I invest my time into? Right, so getting deep insights about what's happening in your toolchain, that should not be any work for you, right? You should get that for free in terms of work. Right? But there's a bit of work to do something with that data. Right? That's only half the equation to have the data. But once you have the data, you can interpret the data, you can make changes, you can run with these changes, and then you can measure again. Right? And you can really see whether the change you made had the impact that you expected. And then you rinse and repeat. Right? So the work really here goes not into collecting data, it goes into working with the data, making experiments to see are the changes you're making actually having the effect that you intended to have. And if you're like on a 5-people team, well, that is maybe even easier to grasp with intuition. But if you're in a team with 100 people, 1,000 people, 2,000, 5,000 people, without the data, there's no chance you will make the right decisions. And also when you want to make a case, maybe to your manager, hey, we need a tool for X, Y, Z. If you don't have any data, you have a much weaker case than if you can say, we see this agent is always failing the builds, something wrong with the hardware, can we please get a new instance? Right? That's much easier to defend if you have that data. Let's take another look towards performance. Formula One, I thought that was pretty impressive. When they go out of the garage on the racetrack, every time they do this, they have more than 300 sensors capturing more than 1 million data points every second. Right? So tons of data. You could say insights are captured about what's happening with the car on the road every second. And all that data is analyzed, processed, and acted upon during a race, during a practice run, or also once the car goes back to make more structural changes. Right. What we see as engineers, though, is we're often not as fast as a Formula One pilot. Oftentimes, we spend time waiting. Right. What do we do when we are waiting? We're context switching. Right, we're doing something else while something else is running and not yet finished. Right? And that leads to a lot of cognitive fatigue. It leads to not being so happy and satisfied anymore with the work we're doing. And it ultimately also leads to less fast delivery of our features. Right? So, and that's something we should address. Right? We need the fast feedback from a tool chain, so we're not waiting. We can stay in the flow. We can do the work step by step, quickly deliver, and then move on to the next thing. But there's more to it, and I think this is pretty interesting. And should not be scared by the screen. But if you have faster feedback cycles, yes, you will wait less time to see whether the change you made is a good change or not. That will lead to less context switching. It will give you more focus because you're switching less. And yes, you will be more productive, but there's more to it. Right? You will also deliver higher quality if you're not juggling between 5 things all the time. Right? Also, if you have faster feedback cycles, you will naturally build more often. You're not going to accumulate those changes over a day because you know, oh, every time I run the build, I will have to wait a few hours. Right? So you're going to build more often. And if you build more often, your change sets are going to be smaller. That makes troubleshooting easier because you have a much smaller set of changes to consider when something doesn't go as you expected. It also leads to less merge conflicts than if you have this big change, which ultimately all lead to higher quality. Also, if your build's feedback is faster, and the build in general becomes faster, you can do more quality checks earlier. Instead of saying, let's do this only once a week, at the end of the week, you can verify more things earlier, get the quicker feedback, instead of having to deal with all the things that come up at the end when actually everything is run and tested, right? Which again leads to higher quality, right? So there's quite a cycle, a positive cycle of things that come from faster feedback cycles. So how can we accelerate those feedback cycles? I grouped it into 4 different things. There might be other ways to achieve it as well. But conceptually, we can avoid work that has been done before. Just like when you type in pi in a calculator, it's not recalculating pi every time. It has done this calculation once and stored it. Right? The same concept here. You run your tests, you run them again, and nothing has changed in your tests or on the class path in general or anything else that goes into these tests. Well, you don't need to rerun them. Or whether it's compilation, Java doc, Coke generation, doesn't matter. Whatever has been done before and created some result, let's just reuse that result. Sometimes you made a change, and so now we need to do the work. But in that case, and that's point 2, let's only run that part of the work that is actually affected by those changes that you made. Right? So if I make a change in the implementation of a method and have a class depending on that class with that method, I don't need to recompile that other class, right? Because it doesn't care about internals of a method. Or if I make a change in a code over here, I don't necessarily need to run the test over there. I might have to, but not necessarily, right? So sometimes it's very deterministic, and sometimes it's more heuristic. But the goal being, let's not do work that is not related to the changes I made, right? And whatever work is left, let's do it in parallel, so we get the feedback faster. And last, let's do the actual work faster, right? Your test might be very slow. Maybe one test brings up half the system to do a very simple verification. If you can make that faster as well, that is another way to accelerate your feedback cycles. And you can combine them. You can use them in isolation or use them together. Right? I used the example below graphically using tests. Right? So let's not run the tests again if nothing changed. But if something changed, let's only run those tests that are affected by the change. And whatever tests are left then to run, let's run them in parallel. And last, let's also make the actual test faster. Give you some concrete examples from open source project. They're using Gradle Enterprise. So for example, Spring. All the Spring projects are using Gradle Enterprise. This is from Spring Boot. So they only build about 100 times a day. It's not a lot it would not be a lot for a commercial product, but it is quite nice for an open source project. So every 24 hours, they're saving 53 hours by not doing work that was done before. Right? Some other CI build already did the work. So another CI build did not have to do it again, or a developer did not have to do it again. Right? And that is just in one day. Right? That's 6.5 engineers. Micronaut Foundation, it's about 85 or so projects, about 130 builds a week. They're also using the Gradle Enterprise. And every 7 days, they save about 5 days in test execution time because they're using predictive test selection, which only selects those tests that are affected by the changes you made. Right. So huge numbers here as well. Or the Chatty project, they're doing a lot of testing, takes 47 minutes. If you run those tests in parallel, you get it down to 16 minutes. And in all these cases, their build, that's a Maven build here, stays exactly the same, right? So you're not making CI changes or anything like this. It's very transparent to the build. All right. We have those acceleration technologies as well. Of course, you can build your own, right? You can build your own cache, you can build your own selection strategy, and some people do, and your own distribution mechanism. If you use the one from us, Gradle task or Maven goals, that's the unit of work, right? So only changes that affect that work unit, that goal, that task will possibly re-execute or not re-execute. It's not on the level of the entire project. It's not related to Git commit IDs or anything like that, right? So very fine grade, which means you get a much better cache hit rate than if it were like something global that makes up the cache key. Predictive test selection, we use a machine learning-based approach that uses historic build data and decides which tests to run based on a change you made. Test distribution, no change to your build, so you don't need to set up CI with all groups that run different types of tests. It's one build, and you just separate the work from there. Now, getting to a fully cacheable build, using these predictive test selection or selection strategies and distributing work requires some work, right? For example, if your tests are inherently not parallelizable, well, you need to invest some time in making them parallelizable. Once they are, it opens up all these doors for distribution on the same machine or, like I just showed, even on multiple machines. So once you apply that, once you invest that little bit of work, you will get a high return, right? You will get faster deliveries because you have faster feedback cycles, and you will also get higher quality for the reasons I mentioned before, right? So the ratio of investment to return is very small or very high the other way around, right? So the return versus the effort is very high. Right. Two last thoughts before I finish here. Optimizing for your productivity of your team, of yourself, should be a productive process as well. Right? If it's not, you're not going to try to improve your productivity, right? You're not going to do it, right? It would be kind of a contradiction to itself. Also, there will always be more to optimize, to improve than you have time available and resources available, right? So you need to make very wise decisions, and that's where the data comes into play. Right? Because then you can be sure you invest your work, if you want to invest work, where you will get the most in return. If you wanted to take a look how this looks in practice, what types of failures are happening in certain areas, how well does these test selection strategies work, you can go to, we have about 20 open source projects all using Grail Enterprise, Spring, JetBrains, Kotlin compiler, the Apache Foundation, Micronaut Foundation. They're all using Grail Enterprise, and it's all public, right? It's you can see all the data, nothing's hidden there, and you can just play around. These are all the URLs you could go to. They all start with GE and then the name of the project. Hibernate is another one, Micrometer, and so on. If you wanted to try out Grail Enterprise yourself, right? You can do this with a Maven build, a Gradle build, or a Bazel build. You don't need to migrate build tools, and you can experience hands-on the data you get and the improvements you get out of the box. Right. Oh, and last slide, not by accident. Many companies are laying off people. Gradle is doing the opposite. We're doing very well, and so we're hiring. So if anybody's interested in a backend engineer, front-end, or dev prod engineer position, they're happy to apply. We're always looking forward to that. Right. And that covers what I wanted to cover. So I hope you take with you. We can save ourselves a lot of work down the road if we're investing a little bit of work now. Right. So it really pays off. To invest some work now for later. Right. That's it. Thank you very much.